In Cisco Networking Academy, Chapter 13 is on ICMP. So here's a quick video about ICMP. So when we're talking about ICMP, first of all, we're talking about now ICMP version 4 and ICMP version 6 for IPv6. But let's just go over some of the general information that you'll want to know. ICMP is a layer 3 protocol. ICMP tests layers 1 through 3 unless domain names are used. So in other words, if you're using network utility, ICMP utility like ping, and you're pinging an IP address like ping 192.168.8.1, you're effectively testing layers 1, 2, and 3 in the OSI model, the physical layer, the data link layer, and the network layer. Now, if you do that same test, let's say, but you ping mywebserver.mydomain.com, well, this is a domain name. So this is going to take DNS. So now you're not just using ping, which is a layer 3 protocol, you're also involving DNS, which is a layer 7 protocol. So if this ping is successful, you're effectively testing layers 1 through 7. If this ping is successful, well, you've effectively tested only layers 1, 2, and 3. So there's a difference there. Now, what about ICMP? ICMP, or the Internet Control Messaging Protocol, makes up for shortcomings in IP. So IP is a best effort protocol that does not include reliability mechanisms. So IP is basically, IP addressing and the IP packet, but it doesn't have error control and it has a lack of messaging mechanisms. So ICMP is like a companion protocol that goes with IP, and it allows some error messaging and some informational messaging mechanisms. There's two types of basic ICMP messages. There's error messages. They report problems that a destination router or host may encounter. And then there's informational messages, or queries, which help get specific information from a router or host. ICMP, it's important to know that ICMP sends notifications, that means error messages or informational messages, back to the original source IP address. ICMP does not correct errors, it simply reports them. And the two main ICMP utilities that you will be using are ping and traceroute. So we'll be talking about them in a second here. Now, the basic structure of an ICMP message, the datagram is called a message, and the basic structure of the header is it has a type field for the type of message, code field, which is kind of like a subtype of the message. It has a checksum, and then in this case, and then it usually has like the optional data or the messaging data down here. Now this is actually the format of a echo request, which is a ping, and an echo reply, which is a pong. And it has not only the type and the code, the checksum, but it also has an identifier and a sequence number that basically are used to map the request to the reply or coordinate the request and the reply, so you know that they're related. And then there's optional data in this field. And here's another example of an ICMP message. So this is a destination unreachable or a time exceeded error message. And it has the type field, the code field, the checksum. It has an unused portion. And then here in the messaging area, you have the original IP header, basically the original packet that caused the error, plus 8 bytes of data in that packet. So this is like you're reporting back the error, and then, by the way, here's the information of the original packet that caused the error. Okay. If we look at the ICMP version 4 message types, you've got here some error types. Destination unreachable error is a type 3. A source quench, meant to slow down if the end device or the destination is getting overwhelmed, they could send a source quench message, which is effectively saying, hey, we need to slow down here. Can't process all of these packets. That's a type 4 error message. A time exceeded, type 11. Parameter problems, there's a problem in the packet, that's a type 12 message, and a redirection, which is a type 5. So these are 5 types of errors. And then queries, the main one that you'll know about is an echo request, which is a type 8, you'll want to know that, and an echo reply, which is a type 0. You've also got a timestamp request and a timestamp reply, address mask request, mask reply, a router solicitation, and a router advertisement, and then the trace route. Now, the trace route utility, there is an experimental upgrade to the trace route utility that used the type 30, but it's not really implemented. So basically most systems are just using the old implementation of trace route, which we'll talk about also. All right, and then ICMP version 6 message types, they're slightly different. You've got destination unreachable, packet too big, time exceeded, parameter problems. You have the echo request and echo reply. Notice the different type numbers for ICMP version 6. Router solicitation, router advertisement. Notice the neighbor solicitation and the neighbor advertisement. So this is used with neighbor discovery. Then you've got a redirect and route renumbering, and there's a bunch of other ones. There's actually a lot more. So if you go to the IANA website, you can see and just search under ICMP, you can find a lot of information about all these different types. And then there's also informational neighbor discovery protocol options, which are also used, and those are used with for DHCP, DHCP version 6, and basically IPv6 stuff. All right, ICMP errors. So here is a destination unreachable error. It's when a router cannot route a datagram or host cannot deliver a datagram. The datagram is discarded, and the router to the host sends a destination unreachable message back to the source host that initiated the datagram. And then these are some of the codes that could be in there along with the error message. So you could have here like network unreachable, host unreachable, code 1, port unreachable, protocol unreachable. Maybe it's fragmentation needed, and don't fragment was set. The destination network is unknown. The destination host is unknown. Notice code 7. So it would be fun to try to practice and see some of these responses, which we can do here in a second. Okay. And then for ICMP errors, you have also the source quench, the time exceeded error message, which would have two codes. Either the time to live was exceeded in transit, and this is where you have the TTL value is decremented to 0 and the packet is dropped, and you would have a time exceeded message sent back. This is used oftentimes with a trace route. So it's used in trace route, time exceeded message. And then fragment reassembly time exceeded. So if you have a packet that's too big and it needs to be fragmented, and if there's a problem putting those fragments back together, you would get this message, time exceeded, the fragment reassembly did not happen in time. Okay, and then you've also got the parameter problems. Let's say there's a problem with the packet. It would have one of these codes. And then a redirection if there was a redirection. Now, redirection is interesting. When there is a more efficient routing choice to a destination, the router forwards the packet and sends a redirection message to the origination host. So one of the things I asked myself was, hey, could I get the router to send a redirect message and get that to work? And I was able to. It was pretty cool. So I'll show you that here. So in other words, what I did was, first is I set this up in Packet Tracer, and I said to myself, could I get this to work? And what I did is I set up this is the scenario. You've got the router here connected to a switch, and then you have two other routers connected to this switch. And the interesting part is R1 wants to communicate over here to this to this interface here on this IP address. So R1 wants to, let's say, ping 172.16.1.1, which is coming off of R3. However, R1 has a route to R2, and then R2 has a route to R3 to get there. Now, this would be a scenario where a redirect message could be sent, because obviously R1 should probably just go directly to R3 to get to this IP address. However, R1 has a bad route or an inefficient route, and the route for R1 goes to R2, and then R2 routes it to R3. Now, what would happen here, R3 responds directly to R1. However, R2 could send a redirect message back to R1 saying, hey, there's a better route to reach this destination. You should go directly to 10.10.3 if you want to get to this network. Don't go to me, go directly there. So that would be the redirect scenario. So I tried to set this up here in Packet Tracer and I could not get the redirect to work. So what I did was I used real equipment, said, hey, well, would this work with, I said basically, would this work with real equipment? And it does. So let's check it out. So in Netlab here, in Netlab I have a similar scenario. You've got R1 connected to a switch, R2 and R3, and notice they're all connected, and I put in the routes, so R1 will route to R2 to get to R3. Okay, and then we could basically take a look at some of these messages. Now, so to get this to work here, basically we can go into R1, and you'll see that if I type enable, and then I type ping, or let's type trace route to 172.16.1.1. Let's see here, we'll run a trace route, and it's going to trace the path that it takes to get from R1 to R3. And we'll see here, it'll show up here in a second. All right, first it went to 10.10.2, which is R2 up at the top. And then it's going to go to 10.10.3. Notice it's sending basically three packets. And each one of these packets, the first three had a time to live of 1. So as it reached router 2, the time to live was decremented to 0. And router 2 at the top sent the time exceeded messages here, and sent 3 of them. And then the next set of 3 packets were sent with time to live of 2. And so it reached 10.10.3 and was able to basically get there. But as you can see, it's working. So if I ping 172.16.1.1, you can see that it works. So not only can I ping from this router to the R3's loopback interface at 172.16.1.1, but it goes through R2 to get there. So essentially, you would think that a redirect message would be sent, and it is. We can see it if we go into here, and let's turn on debugging. So we'll say debug IP and then a question mark, and you can see that if I put debug IP and then a question mark, there's an ICMP transactions debugging that we could turn on. So that's what I'm going to do. So debug IP ICMP. So we turn on ICMP packet debugging, and then this time I will issue that ping to 172.16.1.1, and notice we get this message, and there it is. So the ping was successful. 5 pings were sent, 5 were responded, but notice this first ping. Here's an ICMP redirect received from 10.10.2 for 172.16.1.1, use gateway 10.10.3. So there's the message from R2 saying you should use R3 to get here. And then you can see the corresponding 5 pings. This will also work if I run a trace route to the destination. It just takes a little while longer, but it also works. We'll see it here in a second. Now, if you wanted to see some other types of messages, that's good too. So let's see here. Well, first of all, we see there's time exceeded received. So notice the time exceeded messages coming in from the trace route. So the first sets here, time exceeded arriving from 10.10.2, time exceeded from 10.10.2, and then a third one from 10.10.2. Then there's the redirect message saying, hey, if you want to go farther, if you want to go 2 hops with a TTL of 2, you should go directly there. But anyway, and then, oh, look at that. Here's a port unreachable received from 10.10.3, and another redirect, and then a port unreachable, and it looks like we reached our destination. So you can see these different types of ICMP messages. So another thing that I did that was pretty interesting is I put in the routes, and what I decided to do was I tried to put in deliberately kind of weird routes. So notice here, my route to this network has a /16 subnet mask. So this router is saying any packet destined for 172.16 network, go here. And then this one says any packet destined for 172.16, go here. So in other words, the subnet mask is /16 and /16. However, the network itself is /24. So if R1 tries to ping a bad network, like let's say R1 tries to ping 172.16 2.1, well, R1 will still forward it because the first two numbers start with 172.16, and R2 will forward it because the first two numbers are 172.16, the first two octets. However, when it gets to R3, R3 won't know that there's a 172.16.2 network. It won't know about that. So we should get a message coming back. And let's check it out. So what we'll do is, back in Netlab here, what I'll do is I'll say, what if I was to ping 172.16.2.100? Well, there is no 2 network over there. It's only a 1 network. However, R1 and R2 are just, they'll route anything that starts with 172.16. So we ping it, and we should get a new message, and we do. Well, first of all, there goes our redirects that we get from router 2, but then notice at router at the destination 10.10.3 we get an unreachable message, host unreachable. So in other words, R3 sends back a host unreachable, destination unreachable message because there is no 172.16.2 network. Okay, now another message that we could do is on R3 here. What I've also done on R3 is, if you look in here, take a look at this, I've also put in R3, let's see here, I've put in an access list 100, deny the ICMP protocol from any source to any destination. So that is an access list. So if I turn this on, then it will deny pings, and we should get a different message. So that's what I'm going to do. So I'm going to go into interface gigabit 0/0, and I think that's the right interface. Let's just double check. Nope, it's gigabit 0/1 that we want to do this. So I'm going to go into, hold on, I'll go into global config mode, interface gigabit 0/1, and I'll say IP access dash group, access list 100 inbound. And so now that will activate that access list on the interface of router R3. So now R3 has an access list denying ICMP traffic right here on this interface. So it should get denied. So now if we go back to R1 and we try to ping 172.16.1.1, we should get a different message. And we will. Okay, first of all, there's that redirect. Notice we have debugging on, so we see the redirect from R2. And then there it is. So reply back to 10.10.10.1, administratively prohibited, unreachable, received from 10.10.3. And you can see here, there it is, unreachable. So you can see this is an administratively prohibited unreachable. So once again, it's different codes. So if we look back here, we get on the destination unreachable message, it could be for different reasons, and those will be in the codes. And you can see that also if you're implementing Wireshark and you're looking inside the packets, you would see those in the frame fields. You would see it right here under the type and code. Now, if we want to see, if you want to see something like that in Packet Tracer, what you could do is you could run a simulation here and filter for ICMP in the simulation, and then maybe go over here to R1 and say I want to ping 172.16.1.1, and it'll set up a, notice there's the packet that's going to get sent, and notice if I look into it, outbound PDU details, we can look at the ICMP fields here, and you can see it's a type 8 echo request. And so then we can step through it, and it goes up here, takes the wrong way. However, the correct route goes over to R3, and then as it comes back, when it gets back here, notice this, the return route was a lot smarter. You can look at this inbound PDU detail, and you can see the ICMP code type 0. So this is an echo reply, and that relates to, once again, echo request type 8, echo reply type 0. And then you can get different types of messages. Now, what I was not able to do in Packet Tracer is get R2 to send a redirect message back to R1, because Packet Tracer, this is just a simulator, and so you're not going to get that kind of result. You're not going to get all of the types of results showing up that you would on real equipment. So that's why, if you really want to see some of those details, you kind of need to use real equipment. And that's what I used here in the Netlab, using some real routers in a similar topology.